Okay, so good morning. Today we are going to dive into quantum mechanics, and we are going to discuss the key ideas of quantum mechanics. So now, as I mentioned, quantum mechanics is a theory of probability. What do I mean by that? You see, essentially, we observe a phenomena and we should be able to estimate what is the likelihood. Essentially, a lot of physics is about it. So in physics we have events and processes. So what is an event? Event is whatever occurs. So to make the argument, let's say the event is something that registers on a detector. It can be a photon pinging on a detector. It can be you collecting an electron somewhere. Anything that registers on a detector is an event. And what is the process? Process is the way or alternative by which the event happens. So for example, let's say I have a 50-50 beam splitter, and I have an incoming photon. So a 50-50 beam splitter, half of the times will just transmit the photon and half of the times it's just going to reflect the photon. And I have got these two detectors, B and A, and I make sure that in this experiment there is only one photon at a time. So I make sure there's only one incoming photon. Either it goes this way or it goes this way to either A or B. Then I wait for half an hour maybe, and I repeat this experiment. So what are my observations? Either A clicks or B clicks. And there's a 50-50 chance. They never click simultaneously. And the most interesting part is we cannot predict which of A and B is going to click. So that was so much so about the beam splitter. Now let's compare this to a coin toss. So there is my hand, and let's say I'm flipping a coin. Coin goes up, it does its thing, and it lands somewhere. This is the coin toss. And let's say I had a fair coin, so I have a 50-50 chance of heads or tails. Interesting. So the question that arises at this point of time is, what's the difference between the randomness of the photon beam splitter setup, let me call it detector setup, and coin toss? How are these two randomness different? So that's one of the questions. So maybe we can pause here for a while for you guys to ponder about this point. What is fundamentally different between these two processes? The beam splitter is also a random process. Either the photon goes to detector A or it goes to detector B. And coin toss, I get either heads or tails. So to answer this question, first of all, I think it's a good point to ask, what is the origin of chance, or where is chance coming from in a coin toss? I already have, so what's the origin of chance in a coin toss? How would you answer this question? So what's the answer of this question? Think a bit on this problem. Is there anything fundamental about the randomness of the coin toss? That's my question. Well, the answer, if I may say, is the missing information. To appreciate this point, imagine I have the coin toss. This was my coin. And imagine I had these fantastic CCTV cameras tracking the motion of the coin right from the time I launched it from my hand. So these are CCTV cameras. And let's say I have all the sensors in the world. I have a sensor to measure the torque which my hand puts on the coin when it's getting tossed up. Do you think in such a scenario, when I have all the possible information about this coin toss, is this process still random? Well, the answer to that question is no. The ignorance I have about the coin toss was the cause of the randomness of the coin toss. If I am able to track the motion of the coin toss through the CCTV cameras, if I am able to measure the torque I am applying to this coin, well, then it's a deterministic process, because a coin toss obeys the Newton's laws. It's a deterministic process. Whatever was the apparent randomness of a coin toss was because of my ignorance. I didn't know the torque I applied on the coin. I didn't know the pressure exerted by the air, the velocity of the air molecule, so on and so forth. And hence, assuming it was a fair coin, I said, okay, half the times roughly it's going to be heads, half the times it's going to be tails. So that's the central message, that in classical probability or in classical physics, if I know all the information, well, then there is no 50-50 chance. Now let's compare the same thing to the setup of our beam splitter. So again, there is my beam splitter and my incoming photon. Now I may ask the same question here. Where is the missing information here? Well, the beauty is that there is no missing information. So I can say that quantum mechanically, in this setup, there is no missing information. What that means is that even if I provide maximum possible information, to the experimentalist, this event is fundamentally random. We cannot avoid this randomness. Whereas in a coin toss experiment, let's say you provide me the exact information about the trajectory of the coin or how much torque I have applied to the coin, provide me all possible details, well, then it's a deterministic process. I precisely know how it's going to land on the table. So we've already seen a fundamental difference between quantum mechanics versus classical mechanics. And the essential difference is difference between something we call subjective versus objective. So classical randomness is in some sense subjective. Subjective. It's due to the missing information that in principle can be supplied. Whereas quantum randomness is something inherent. Something intrinsic to the system. And the essential part is that this randomness is random for all observables. For all observers. So classically, let's say someone was cheating, he had some sophisticated cameras. Well, he exactly knows where my coin is going to land. Whereas for you guys, it's a 50-50 coin. Or let's say I'm playing a game of cards and I am dealing honestly as possible. You calculate what's the probability of getting a jack, a king, or a queen in a game of cards. But for someone who's cheating, he has all the maximal information about the process. Well, for him, it's a deterministic process. It's no longer gambling, it's cheating. So there is a subjectivity associated with classical randomness or classical physics, and that is because of the subjective knowledge of different observables. What we have seen quantum mechanically, even if I supply the maximum possible information to the experimentalist in this experiment, I cannot avoid the randomness. I won't be able to predict which of the detectors A or B is going to click. Randomness is unavoidable. So let's explore this more with our photon and a beam splitter. Let's take the setup again. I have a photon, an incoming photon, to a 50-50 beam splitter. And let's say I have two mirrors. And over here I have another 50-50 beam splitter. And I have two detectors, A and B. So photon comes, either it goes this way, gets reflected, goes to this beam splitter, or it goes this way, gets reflected, goes to this particular beam splitter. Mirrors just completely reflect the photon over here. So this setup, when I have two beam splitters in a mirror, this is called as a Mach Zehnder. Interferometer. So again, we can ask the same questions. What are the chances that detector A clicks? What are the chances that detector B clicks? And remember, I have only one photon at each time in the experiment. So I fire a photon, wait, let one of them click, wait for some time, then I again fire a photon. So at any point of time, there's only a single photon in this particular experiment. So the idea is to calculate which of the detectors with what probability is going to click. So in order to calculate the probabilities, let's see what are the paths the photon can take. So I'll again draw the beam splitter. Okay, so either the photon, one possible path for the photon is it goes this way towards detector A, or it can go this way towards detector A. So just towards A, the paths taken by the photon are this or this. And when I have two ways of doing a thing which are mutually exclusive, I just add the probabilities. So the probability of event A. So event was the click of the detector A. The probability of event A is, let me call this 1 and this 2. So I have, in computing the probabilities, I have probability of 1 plus probability of process 2. And since it's a, how are you going to calculate the probability? So at this point, the probability of going this way or this way was half-half. So I have half. And then over here, again at this beam splitter, the probability of either going this way or to the detector B or to the detector A, it's again half-half, 50-50 probability. So the probability of event 1 is going to be 1 upon 2 times 1 upon 2. This is going to be this process and this process, both of them have to occur simultaneously for 1 to occur. For 1 to occur, it has to pass through the beam splitter. That has a 50% probability. And then over this beam splitter, it has to get reflected. That is again 50% probability. So when I have a process that can be broken down, then the probability is going to be this event and this event, they're going to be multiplied. Similarly, for event 2 to occur, this event to occur, I have a half-half probability of going this way, and again a half-half probability of not taking this path but taking this path. So I have, which gives me half. So in other words, the probability of the photon being detected at the detector A is sum of 1 and 2, which comes out to be half. So roughly half the times I'm going to detect, exactly half the times actually, I'm going to detect the photon at A. So are you all happy with this thing? We are just calculating the probabilities. What was the probability for this process as well as this process occurring? And we can also, simultaneously calculate, let me paint it by black. So the probability of B is going to be this path the photon takes, or the photon takes this path. So that's going to be, again, I'm going to get the probability. So since either the photon is detected at A or B, so the probability I get for event A, the detector A to be clicked, if it is half, then the probability of detector B going to be clicked is also half. So I hope everyone is happy so far. So here the question is that is my analysis correct? Well, when we do the experiment, unambiguously it is wrong. What is observed is probability of A is 1. Welcome to quantum mechanics. So if you are baffled by it, there was nothing wrong in calculating the probabilities. We just used the rules of probability. How we know that? We just had an event, either it could occur one way or the other way. We just added the probabilities and got half as the answer. But the beauty is in the experiments. When we do this experiment, the probability of detection at A is 1. So think what went wrong. How do we make sense of it? So the answer is in, well, so why should I give you the answer right now? Just pause here for a minute and think about it. I mean, this is something really baffling, at the same time very, very fascinating, and essentially this is at the heart of quantum mechanics. What went wrong in our analysis over here of the beam splitter? Why this seemingly innocuous beam splitter, it's giving the probability of A, detection A to be a certain event, and the detection of B is 0. Well, the answer lies in probability amplitudes. let's assume we have all the information about the system as we've discussed. The experimentalist is supplied with all the information about the system. So quantum mechanically, what we say or how we make sense of this thing is that an event has a probability amplitude associated with it. Let's call it psi. And the probability is given by probability of event is given by the modulus squared of it. So an event has a probability amplitude which is a complex number generally associated with it, and the probability of that event is just the absolute value squared of that. Now you can take this as rule 1. Now if an event can occur via two indistinguishable processes, and each process has amplitudes psi 1 and psi 2 respectively, then the total amplitude of the event is the sum of individual amplitudes. So psi total for the event is psi 1 plus psi 2. So for example, in our Mach Zehnder interferometer, photon took two indistinguishable paths. We are going to define indistinguishability in a moment, but photon took two indistinguishable paths. And hence we added the probability amplitude, which is a complex number of detection at A, to be the sum of both of them. So again, if I can draw them over here, yeah. So essentially, I associate a probability amplitude psi 1 with 1 and psi 2. And since the detection at A could either happen through this path or through the going through the upper arm of the interferometer, I add psi 1 and psi 2. And the probability now of A is simply given by the absolute square of this, which is nothing but psi 1 plus psi 2 modulus of squared, which is psi 1 squared plus psi 2 squared plus psi 1 psi 2 complex conjugate plus this term. So as a comparison, classically we add up probabilities. Remember, if you look closely at what we did in our analysis, we exactly did this. We went here, we took the probabilities of 1 and probability of 2 and we added up the probabilities. That's what our classical intuition tells us, that if event can happen through two different processes, I add up the probabilities. The chances just add up for events which can happen through two different alternatives. Quantum mechanically, we add up probability amplitudes. And the final probability, of course, is given by the absolute square of them. So I'll just write, we add up probability amplitudes. And the probability is given by adding up. And this is called as interference. So coming back to our Mach-Zehnder setup, for event A, psi 1 psi 2 star plus psi 2 star psi 1 star is equals to plus half. And that's the reason why when we added the probabilities, it came out to be 1. For event B, psi 1, let me call it B, let me call it A, doesn't really matter. The A subscripts are, we are calculating the probabilities for A. The cross terms, so to speak, that comes out to be minus half. And that's why the probability of B was equals to 0. So doing it more explicitly, probability of event A was psi 1 square in the figure below plus psi 2 squared plus psi 1 psi 2 star plus psi 2 star psi 1. Sorry, this should be 1 and this is 2 over here. So we were happy thinking that, okay, we got 1 over 4 plus 1 over 4 and this was the only thing we calculated. We did not take into account these cross terms or the interference terms, which for the event at A, this was exactly equals to half, since this whole thing came out to be 1. So the probability of detection of A because of this interference turned out to be 1. So, and subsequently the probability came out to be B. So I'm not filling in the numbers. That's for you to do in one of the homework questions, how these things work out. But that essentially is one of the founding rules of quantum mechanics. Remember, quantum mechanics is a theory of probability, but unlike ordinary probability, where we add the probability of processes when an event can happen through process 1 or process 2, in quantum mechanics, we do not deal directly with probabilities. We deal with something called the probability amplitudes, and then the probability amplitude of the event is the sum of the alternatives. And finally, to calculate the probability, we have to sum over the amplitudes and then calculate the probability. So that's the essential and the key difference between quantum and classical physics. So I guess it would be good also to define the notion of indistinguishability here. Remember, we said that if two processes are indistinguishable, we add the probability amplitudes. So what does this indistinguishability mean? So the processes are indistinguishable. We call the processes are indistinguishable when there is no information anywhere in the universe, and by universe I mean the entire universe, to distinguish them. Well, processes are distinguishable when there is information in the universe. Which alternative happened? So in the case of our photon experiment, which path towards this event registering at A, which alternative did the photon take? Either it took the lower path or it took the upper path. No one in the universe knows this, and hence when no one in the universe can distinguish between two alternatives towards the outcome, which in this case was the detection event at A, we add the probability amplitudes. So now the question arises that is there any way to see which of the alternatives happen? So we'll again draw the Mach center interferometer. I have an incoming photon. I have a beam splitter usually my mirrors. So let's consider the detection at event A. Is there any way I can detect whether I went through this route or I took this route? So let me put some device over here to detect if the photon took the upper arm of the interferometer, and I would call that device something called as the Pokel cell. So essentially the feature of the cell is that voltage develops across this cell when the photon passes through this path. So voltage, I'm just making my notes a bit neater, develops across this cell. We know which path the photon took. What happens in this case? Suppose I repeat my Mach center interferometer experiment. I have one photon coming. I have a Pokel cell in one of the arms. What do you guys expect? What's going to happen? So what's going to be the probability at A now? Mind you, I made the paths distinguishable. As soon as the photon passes through this path, I'll have a voltage develop across. Any guesses what happens? Well, the answer is 50-50. So the probability of A is half, the probability of B is half. Remember, when my paths were indistinguishable, I was adding the probability amplitudes. And the final probability given was this guy. When I make my paths distinguishable, I just add the probabilities, which I already calculated to be, came out to be half. So there's a very intimate connection between when my alternatives in the universe are indistinguishable, that means there's no information in the universe at all which path the photon took, then in this sense I'm going to add up the probability amplitudes, and that's essentially the key ingredient of quantum mechanics. The moment anyone in the universe, it could be the air molecules, it could be anyone in the universe comes to knows which path the photon took, I'm going to add the probabilities, and my classical logic is restored. So this is something really fascinating about quantum mechanics, and so I think we are almost done with the time. So we'll continue this in the next lecture. Stay tuned. Thank you.